Hi. So far we have covered 3 modules. Okay, so remaining 2 more modules are there. Now these 2 modules contain an important concept called transforms. Okay, so we have 2 transforms to study. One is called Laplace transform, which will be dealing with this module, and also another one called Fourier transform, which will come shortly. Okay, so before we start the study of this Laplace and also Fourier transform, what is a transform first of all? Okay, so transform is basically a tool which helps you to simplify problems. Okay, so transform is basically a tool which will help you to simplify some problems. Okay, suppose you have a complex problem, you have a complicated problem which you cannot solve using direct methods, or the methods which are used are actually very difficult. So what I will do is that I'll actually make it simpler by means of a transformation. Okay, so such an approach is called a transform method. Okay, for example, and this is the diagrammatic representation of that thing. Suppose I have a original problem which is very difficult to solve directly, and I need a solution to that original problem. Okay, so I need a solution to that original problem. So direct solving is actually very difficult, or it is not possible. So what I will do is that I'll actually transform this. I'll actually transform the original problem into a new problem. Okay, so that problem would actually be a simpler one. So what do you mean by this transform? Transform is a very simple thing. Suppose our original problem depends upon some variable x. I'll just change this variable x to some other variable, say s, by means of some function. Okay, suppose your x is something, I'll put x is equal to some maybe e raised to s log x, etc. something. So I can put some many functions like that. So I'll just put some x is equal to some value, some other function, convert this x to another variable, say s. Okay, so now the problem is in terms of s. Okay, so when I convert it, actually what happens is that suppose the original problem is very difficult integral, it will now actually become a simpler one here. Okay, so once I convert it to this s, what will happen is that it will be very easy to solve it in terms of s. Okay, so so when I convert it into a simpler one, it will be very easy to solve there. I'll find the solution in terms of s. I'll find the solution in terms of s. Then what I'll do is that I'll give back the value of s in terms of x. I'll get back the inverse transform. Okay, so just like our Euler-Cauchy equations, we had to solve in the Euler-Cauchy equations, it was x square y double dash plus xy dash, etc. You had, I think you remember this equation. So in order to solve that, what did you do? I gave a substitution for x. I called it as x is equal to some e raised to z or something like that. So I gave a substitution and I converted that differential equation in terms of z. Then it was easier to solve because you had a differential equation with constant coefficients. You solved there. Once you solve that, you can come back to the original equation by giving back the value of that z. So the same technique is being applied here. Okay, so you will have an original problem. You will actually transform it into a transform space. So basically Laplace transform and also this Fourier transform are integral transforms. That means here the function is actually an integral. So there are many transforms are there. So Laplace transforms and Fourier transform basically integral transforms. That means your x will be some the substitution for x will be some in terms of some integral. Okay, that is what is called integral transform. Okay, so it's basically an integral transform means you are giving a function which is in part which contains an integral. Okay, so I'll just use that function to convert it into a simpler one. I'll solve it there. Once I solve it that, I'll again give back the original value of that to get the original solution. Okay, so that is the method of these transforms. Okay, that's a basic idea. You'll understand more about this method when we go deeper into the theory of Laplace transform. So this is just an indicative idea what we are going to do. So you will have to study many things here. You need to know what is a transform. So once you know what's a transform, you should also know how to get back. Okay, so once you know how to take a transform, you should also want to know what do you mean by an inverse transform. So these two concepts you will be studying, and also you will study how to convert some equations to Laplace transform. You will have to convert some equations in terms of this Laplace transform, how to solve them there, and how to take back the inverse transform. So you will be studying 3 things here. You will be studying what is a Laplace transform, then how to convert equations, how to solve the equations there, and then how to get back to the inverse one. Okay, so these 3 concepts we will be studying in this section. So this is a brief overview. So we'll move forward. Now Laplace transform is basically known in the name of Pierre Laplace. Okay, here's the French mathematician. Okay, and this Laplace transform is basically used to solve differential equations or in particular initial value problems. Okay, so you will be actually solving initial value problems in this course. Okay, so it is very easy to solve initial value problems using Laplace transforms. Okay, the idea is that if you take the transform of differential equation using Laplace transform, it will be converted into a simple algebraic equation. Maybe it will be converted into a a quadratic equation or a cubic equation which is easier to solve. So you will know how to find the roots. From the roots you can write down the solution. Okay, so you are converting a differential equation into an algebraic equation. That is a quadratic equation or a cubic equation which is easier to solve, and once you find the roots you can easily find out the solution to the original differential equation. Okay, so you are actually converting the problem in differential equation to a problem in algebra. Okay, so that is what we are going to do here. So we'll understand this method better when we'll have the application. We'll have to do with the solution of initial value problems using Laplace transform, and you can see that it is much simpler than using a direct differential equation. Okay, so that is the idea which we are going to do here. So, and also all sorts of functions. So some discontinuous functions or some functions which are used in electrical engineering, something like that, or mechanical engineering, etc. With some functions which has a very large magnitude and which acts on a very short second of time. So you will have some functions like that. They are called impulse functions. So those functions, etc., we'll be studying, and we can actually find the solutions, the equations which contain those functions using Laplace transform. Traditional methods of differential equations are not applicable here. So those functions, those complicated functions, can also be studied using Laplace transform. So we will understand it better when we study impulse functions, which we have a section in this module. Okay, so this is the idea. As I told you, you have an initial value problem. It will be converted into an algebraic problem, and you will find the roots there. So once you find the roots, you can find back the original solution. Okay, so it has three step process. One is taking the transform, then solving that algebraic equation, and then you taking the inverse transform. Okay, so it's a 3-stage process. Okay, so so we start with the applications. Let us try to understand what's the definition of a Laplace transform, and we'll also try to find some Laplace transform of some elementary functions which we can use later. Okay, so let us start now. Okay, so the definition is a very simple thing. So basically one thing you have to remember here is that here we will be considering functions as f of t. It's a basically convention. Instead of f of x, I will be taking functions as f of t. That means I'll take function as sin t, cos t, etc. Usually used to take sin x, cos x, etc. Now I will be considering with t. Okay, why is it so? Because in most applications it will have to deal with applications involving functions which depend on the time t. Okay, so that is the idea. So because of that convention, you usually take functions as f of t only. Okay, so actually we will take functions in the time. We should say that this Laplace transform converts functions in the time domain. Okay, so because functions containing the variable t to some other function. So because of that convention, I will be taking the function as f of t instead of f of x. Okay, so I will be considering function as f of t. So let f of t be a function like that. So let f of t is a function defined for all t greater than or equal to. Then the Laplace transform is defined as, you will write Laplace transform as L of f of t. Okay, so this is the notation L of f of t. Okay, so if you want to find Laplace transform of sin t, I will write it as L of sin t. So I hope you understand notation. Simply L of f of t, and it is defined as simply integral 0 to infinity e raised to minus st into f of t dt. That is the definition. Okay, so remember once again, try to study it now itself. What is the meaning of that? It's actually integral 0 to infinity e raised to minus st into f of t dt. Okay, so this is the definition of Laplace transform. For example, suppose you need to find the Laplace transform of sin t. How will you find it? It is simply integral 0 to infinity e raised to minus st into sin t dt. Okay, so this is how you find the transform. So this is the definition of the Laplace transform. Okay, and you can see that once you do the integral here, okay, once you do the integral, this integral is in terms of t. So you will be integrating, and then you will be substituting these limits, and you will be getting a function which is in terms of this s, because s is a constant in this integral with respect to this variable t. So when you find the final function, you will be getting a function of s. So this is called f of s. Okay, so when you take Laplace transform, you will be getting a function in terms of another variable called s. So you are actually converting a function in the t domain to a function in the s domain. Okay, so always your Laplace transform would contain this a variable s, and the original function would contain the variable t. Okay, now you will be thinking that this is actually making things more complicated, because you have a very big integral here which is an improper integral which ranges from 0 to infinity. So how do you think that it is going to make things simpler? Okay, so the idea is that you will never be using this direct definition anywhere. You will not be using this direct definition anywhere. Okay, so you will not be using this direct definition anywhere except for finding some elementary functions. So what I will do is that we will be forming a table Okay, so we'll devise a table for our reference. We'll actually construct a table for reference which contains a function and its transform, and we'll be studying that table. Okay, and referring to this table only, we'll be doing all the problems. Okay, so there is no need to do the integration with respect to this integral 0 to infinity e raised to minus st f of t dt directly in applications, because it is very difficult to compute that. Okay, because it is an improper integral and it has many conditions to access. So we will not use the direct method. The method we are going to use, that we are actually going to construct a table by means of which we will be able to solve the problems. Okay, so we'll be constructing a table. We'll do that later. Okay, so don't be don't be afraid of this. In this weird looking integral, we will never be using that. We will be constructing a table which I will show you shortly. Okay, so I hope this is clear. And some more notation I'm telling you, and this L of f of t is called the Laplace transform, as you know. Okay, and it is actually of the form f of s, and now the original function f of t is said to be the inverse Laplace transform of f of s. That is one convention you should know. Okay, so once again I'm telling you, this f of t, the original function, is there, and if you are taking the Laplace transform of this, you will be getting L of f of t, which is actually your f of s. Okay, now if you want to come back to f of t, we'll say that this the original f of t is said to be the inverse Laplace transform of this capital F of s. Okay, I hope this is clear. So one more thing, the capital F of s is the Laplace transform of f of t, and similarly on the conversely, the small f of t is the inverse Laplace transform of capital F of s. Okay, I hope it is clear. So the given function f of t is called the inverse Laplace transform of L of f of t, or our f of s. And the inverse Laplace transform usually denoted by the symbol L inverse of f of s. Okay, so for Laplace transform it is simply L of f of t. For inverse Laplace transform is simply L inverse of this capital F of s. L inverse of this capital F of s. Okay, so that is just basically convention. When we do the problems, you'll understand it better. So you will be only studying the table for Laplace transform. From the table itself, you can study the inverse Laplace transform also. We will demonstrate that in problems. Okay, so that is so far with the definitions. Now let us get back to our work zone. So that's it. So let us do a problem now. Let us find Laplace transform function f of t is equal to 1 for t is greater or equal to 0. So before that, remember one thing. Here actually your Laplace transform is, your function is from integral 0 to infinity. So your function is defined for all t greater or equal to 0 only. So for t less than or less than 0, we are not interested. Always your function domain is t greater or equal to 0. Always remember that. Okay, just for your understanding I'm telling you. Okay, so suppose let us find the Laplace transform of the function f of t is equal to 1 for t greater or equal to 0. Okay, so before that, let me just tell you that this function is not your constant function 1. This is not that function. Your constant function 1 is this function. If you can see this is that function. This function here is not, it's a part of that function, which is basically this one only. Only this is defined, only this part is there, because your t is greater or equal to 0. This is your function which you are going to define here. Okay, now we want to find the Laplace transform of this function. So how will you do that? Okay, so let us write down the definition. What's the definition of that? The definition is L of f of t is equal to integral 0 to infinity e raised to minus st into f of t dt, right? That is the definition. I am just applying the definition. Only for some simple elementary functions we will be doing the direct definition, and rest every functions we will be devising a table. Okay, so this function is simple, so we will directly do it. Okay, so how will you find the answer now? So it is simply integral 0 to infinity e raised to minus st into your f of t is actually 1 dt. Okay, I hope this is clear. Okay, so what that is simply integral 0 to infinity e raised to minus st dt. Now how will you integrate this? So you know that the integral of e raised to x is e raised to x by a. So you will be getting here as e raised to minus st by minus s in the limits 0 to infinity. Okay, now we apply the limits. You will be getting one thing as e raised to, when you apply infinity, you will be getting as e raised to minus infinity, which is again 0, minus e raised to 0. E raised to 0 is 1 by minus s, which is actually 1 by s. So this is the value. Okay, so you will be getting this. I'll write it like this. You will be getting it as e raised to minus infinity by minus s. Okay, e raised to minus infinity s, it's actually minus infinity s by minus s, minus then 1 by minus s. This is how you will be integrating. But you know that the value of e raised to minus, what's the value of e raised to minus infinity? The value of e raised to minus infinity is 0. Why is it so? Because you will be getting 1 by e raised to infinity, you will be getting the value of 1 by infinity, which is 0. Okay, so that is how the 0 came here. Okay, and one more thing is that this is valid only if your s is greater than 0. This is valid only if your s is greater than 0. Why? Because if your s is less than 0, your minus infinity into s will be actually a positive quantity. So that means you will be getting here as a very large quantity here. So this is not valid there. Okay, so this is valid only if your s is greater than 0. If s is less than 0, this is not valid. Okay, and even if s is equal to 0 also, your 1 by s, the function is not valid. So you always will take that your s is greater than 0. Okay, I hope this is clear. So this this is how we are going to do it. The expression is here. So if n of t is equal to 1, you will be doing this. You will be getting e raised to minus st into 1. So it is simply e raised to minus st by minus s in the limits 0 to infinity. That is actually e raised to minus infinity, which is actually 0, provided your s is great positive. Otherwise it will be simply infinity. So it is not, integral will not be defined there. Minus e raised to 0 is 1 here. So it is actually 1 by minus s. So you will be getting the final answer is 1 by s, where your s is greater than 0. So always remember, Laplace transform of 1 is 1 by s. So we have actually devised the first row of our table. Okay, so we are going to construct a table of Laplace transform, and the first entry of the table is actually 1, and we have found the first entry of that, which is actually 1 by s. Okay, I hope this is clear. Let us do one more problem here. So let us do one more problem. Let us go for another function e raised to at. Okay, so here also your function is always for greater than or equal to 0. How will you find it? So write down the definition now. What is it? L of f of t, which is simply integral 0 to infinity e raised to minus st into f of t dt. Okay, straightforward definition. It is actually integral 0 to infinity e raised to minus st into e raised to at dt, or you can write it as 0 to infinity in e raised to minus s minus a t, right? S minus a into t dt, because a raised to mx plus a raised to nx is a raised to m plus n into x. Using that concept is simply e raised to minus s minus a t dt here. So when you integrate, what will you get? You will be getting this as e raised to minus s minus a t by minus s minus a in the limits 0 to infinity. So when you substitute infinity, you will be getting it as 0, minus when you substitute 0, you will be getting as 1. So you will be getting it as 1 by minus of 1 by minus s minus a, which is simply 1 by s minus a, provided as earlier your s minus a is positive. Okay, so when you integrate, you will be getting it as e raised to minus s minus a into infinity by minus s minus a, minus you will be getting e raised to 0. So it is 1 by minus s minus a. So this is actually 0, provided this s minus a is positive. So you will be getting this as simply 1 minus s minus a, where s minus a is greater than 0. Okay, so as I told you, the Laplace, so we have got the second one now. Laplace transform of e raised to at is just 1 by s minus a, and Laplace transform of 1 is 1 by s. So we have found two values of our table. So I hope this is clear. Okay, so this is the computation work here. So provided this is minus a is greater than 0. Okay, now we will discuss some theorems which will be helpful for us to find Laplace transform. So before that, does Laplace transform exist for all function? So as we saw, the existence and uniqueness theorem in the case of differential equations, here also there is a problem of existence and uniqueness of Laplace transform. So will Laplace transform exist for all functions, and if it exists, is it unique? So the same condition is here. So in the syllabus they have mentioned you to just the statement of existence and uniqueness theorem. So you have to just study the statement only. There is no need for proof, and there is no need of application also. Just try to understand this. So very simple thing. This Laplace transform will exist for a function which is bounded, okay, by some value. So that is the idea here. Suppose f of t is a piecewise continuous function. So I hope it is continuous. You know the meaning of continuous function. You can draw it without a break. And what do you mean by piecewise continuous function? So piecewise continuous function is a function which has some discontinuities, but only finite number of them are there. So it will be like this. So it will be like this. So it can have discontinuities, but they are finite or countable. So it is not necessary for you. Just understand it's a piecewise continuous function. Okay. in the real line from 0 on the real line from 0 to infinity, on the real line from 0 to infinity. That is what you mean by semi-axis. So don't be bogged down by this terminology. You can write it in your own words. And the main condition here is that it is bounded. This f of t should be less than or equal to some constant m into e raised to kt. So if that condition is satisfied, we can say that the Laplace transform exists and is unique. So Laplace transform will exist depending upon a bound called f of t is less than or equal to m into e raised to kt, where this m and k are constants. This is just for information purpose only. You don't want to go about the detail about this because it's not required for you. It is beyond your scope of your syllabus, so it is not required. So they can ask you state the existence and uniqueness theorem. They haven't asked it yet, but still they can ask you. So just try to know this definition. Only thing is that remember to write this bound here. Rest everything you can write it in your own words. That is one theorem. Okay, and another important theorem which can be asked and proof you should know is the linearity of Laplace transform. Okay, so what do you mean by linearity of Laplace transform? Very, very important in applications. You should understand this theorem better. So what do you mean by that? Okay, so what do you mean linearity? A function is linear. So basically it's a simple thing only. That is, if I want, suppose I need to find the Laplace transform of two functions f and g. So I need to find Laplace transform of this f plus g. Okay, you may have studied this in linear algebra, like linear transformations there, the same concept here. So this L of f of g is simply L of f plus L of g. Okay, so a function which satisfies this property is called linear function, and Laplace transform satisfies this property. Okay, so what do you mean by that? Suppose you need to find Laplace transform of f plus g. What you can do is that you can directly find it out, or you can, if you know the Laplace transform of f and if you know the Laplace transform of g, you can simply add them. So that is what is meant by linearity of Laplace transform. Okay, so many functions are linear. You suppose your derivatives of linear. For example, derivative of that f plus g is actually f dash plus g dash, and integral of f plus g is simply integral of f plus integral of g. Okay, but all functions are not linear, because if you take the squaring function, for suppose you want to find x plus y the whole square, it is not equal to x square plus y square. So there are functions which are linear, there are functions which are not linear also, but your Laplace transform is a linear function. Okay, that's one idea. And one more thing is that there's one more property for this linear function. Suppose you need to find Laplace transform of some constant into this f. Okay, then also you can take this constant outside, that is called constant into L of f. This is also a property of linearity. Okay, for example, you know that derivative of 2x is 2x, derivative of 2x is simply 2 into derivative of x. Or integral of 2x is simply 2 into integral of x. So derivatives and integrals has a linearity property, but square of 2x is not 2 into x square, it is 4 into x square. So there are functions which satisfy this property and functions which do not satisfy this property also. But Laplace transform satisfies the property that the Laplace transform of a constant into this function is simply c into L of f. That is the property of linearity of Laplace transform. Okay, so you should write this together like this. Both these properties which I told, usually will write it together like this one. That is, I already told that L of f plus g is simply L of f plus L of g. Similarly, L of some constant into f is simply c into L of f, or you can write this thing as together as L of some a in constant into f of t plus b into g of t. Simply, first of all, I can write this as L of a into f of t plus L of g into b of t. From there, I can write this a into L of f of t plus b into L of g of t. That is what is meant by linearity of Laplace transform. So they can ask you state and prove the linearity property of Laplace transform. It's a very simple thing. I hope you understand this idea. We will be using this idea again in applications. So first try to understand this thing. So I will prove this one. So the proof is also necessary for you. Let us try to prove this. Okay. Suppose I need to show that. So before we go to prove, I need to show that L of this AF plus BG is simply equal to A into L of F plus B into L of G. Okay, actually this follows from the linearity of integrals only. So what is this L into AF plus BG? Your L into AF plus BG is simply, I am going to apply the definition, just simply integral 0 to infinity e raised to minus st into AF plus BG dt. Okay, this I can write as integral 0 to infinity e raised to minus st into AF dt plus integral 0 to infinity e raised to minus st into BG dt due to the linearity property of this integrals. Now we can take the constants outside, that is integral a into integral 0 to infinity e raised to minus st into f dt plus b into integral 0 to infinity e raised to minus st into this g dt. Okay, that is simply your a into L of f plus b into this L of g that satisfies your linearity property. Okay, so it's straightforward calculation or odd calculation which we can usually do. Okay, so next we will be using this problems in applications. Okay, let us know. So before we go to the applications, we know two things now. Laplace transform of 1 is 1 by s, and the Laplace transform of e raised to at is simply 1 by s minus a, and also we know the linearity property. So using these things, let us do some applications. So the first application is hyperbolic functions. Okay, so I hope you know what's hyperbolic function. What is hyperbolic function? What is cos hat and then your sin hat. So what's the definition of cos hat? I hope you understand this. From calculus you know that it is e raised to at plus e raised to minus at by 2, and sin hat is simply e raised to at minus e raised to minus at by 2. Okay, so these are the definition of hyperbolic function. Now let us try to find the transform these things. So what is the transform of L of cos hat? Suppose I need to find the Laplace transform of L of cos hat. One way I can do is that I can straightforward using the definition I can go for that is cos hat into e raised to minus st into dt. I don't know how to do this integral. It's very difficult, so it's not possible using that method. So we will be using a slight approach using our applications. So what applications we know? Well, we know the definition of this cos hat. What is it? It is simply L of e raised to at minus e raised to minus at by 2. That is the definition. All right. Okay. Now you know that this we know we have two properties at our disposal. The one is L of 1, then you know the value of L of e raised to at. Okay, and also you know the linearity property, that is L of f plus g is simply L of f plus L of g, and also you know that L of some constant f is simply c into L of f. So you can see here that 2 is a constant here. So can I take 2 outside using linearity property? So it will be simply become L of 1 by 2 into L of e raised to at minus e raised to minus at. So I hope this is clear, because your 2 is a constant here. I have applied your linearity property here. Okay, so once you have done this, again you can apply linearity property again, because here it's a function like f plus g or f minus g here. So it is again 1 by 2 into L of e raised to at minus L of e raised to minus at. Okay, why is it so? Because I have applied the property that L of f plus g is simply L of f plus L of g. Even if it is minus also, it's valid also, because you know the proof also itself, if it is plus or minus also, it is valid there. So I can split it into 2. Don't forget the brackets here. Okay, so now we have got that as your L of cos hat. Now we have got it as 1 by 2 of L of e raised to at minus L of e plus, sorry, it is not minus here, because cos h is plus here, so it is plus 1 here. So sorry here, so it's plus here. So in sign, when you take it, it will be minus. So okay, so it's plus here. So we'll be getting L of e raised to at plus L of e raised to minus at. Okay. Now, again what will you do? Already you know the value of L of e raised to at. So from the, you have a table with 2 entries here. What's the value of L of e raised to at? It is simply 1 by s minus a. Okay. Plus, what's the value of L of e raised to minus at? In the place of L a, you have minus a here. So what will you do? So instead of 1 by s minus a, you will have 1 by s minus a, which is simply 1 by s plus a. There is no need to evaluate again, because in the place of f now you have minus a. So you in the place of s minus a, you will have s minus a, which is simply s plus a, that is 1 by s plus a. Okay, so so you will be getting this. So when you simplify this, you will be taking the LCM, you will be getting this as s plus a plus s minus a, that is actually 2s by s minus a into s plus a, that is s square minus a square, or simply s by s square minus s square. Okay, so I hope this is clear. L of cos hat is simply the value of L of cos hat is s by s square minus s square. Okay, so how will you do that? First you gave the applied definition of cos hat, which is this one. Then you applied the linearity property. You took 1 by 2 outside. You split them. Then you give L of e raised to at plus L of e raised to minus at. You know the value of L of e raised to at from the table. That is simply 1 by s minus a. Similarly, a raised to minus at also you know. In the place of a, you have minus a. So it is actually simply 1 by s plus a. So we'll combine them, taking LCM, we'll be getting this value. Okay, I hope that is very clear. Okay, so similarly, can you find the value of sin hat also? Again, if you want to find L of sin hat, it is simply L of e raised to minus 8 into e raised to minus 80 by 2. So that is actually, how will you get it? 1 by 2 into L of e raised to 80 minus L of e raised to minus 80, right? Okay, don't forget the brackets. So it is actually 1 by 2 into 1 by s minus a minus 1 by s plus a here. Don't ask me why s plus a is coming. Now you should know, because I am replacing a by minus a there. So it is actually s plus a minus s minus a, that is actually 1 by 2 into 2a there, s square minus a square, which is simply a by s square minus s square. Okay, so I hope that is also clear. So now we have a table. Now how many values you have? So you have table with 1 is there, e raised to 80 is there. Now you have got cos hat, you have got sin hat. Okay, so a1 it is 1 by s, e raised to it is 1 by s minus a, cos hat is s by s square minus a square, sin hat is a by s square minus s square. Okay, now I will write cos 80 sin 80. Okay, so if I want to give you a shortcut, I will say it directly. For cos 80 is simply it is s by s square plus a square. We will derive it now, but it is s by s square plus a square. And sin 80 also, I hope you can guess it now. What is it? It is basically a by s square plus a square. Okay, so that's it. So your cos 80 will be deriving it now, and sin 80 also we can derive it. It's very simple thing. Okay, so there are many ways to, so let me tell you one more thing. In Laplace transform, when you are finding transform functions, there are many methods to find a transform. Okay, suppose you are given a function, you can find the transform of it by direct integration, or by using some techniques like this, or by using other methods also. But you can use many methods to find the transform for the same function. Okay, all the methods will be correct, but the transform will be the unique one. It will not be different. Okay, so you can use any method to find transform. Okay, so we'll be using the sine and cosine function here. So let us try to find the transform of sine 80 and cos 80. So there are many methods is there. One method I am going to give you as a homework, which you have to do it there. So if you have studied complex numbers, I hope you know what is the value of cos theta. Cos theta is e raised to I theta plus e raised to minus I theta by 2, and your sine theta is e raised to I theta minus e raised to minus I theta by 2i. Okay, using the de Moivre's theorem, this. So if you know value. So if you, what is your cos 80, then your cos 80 would be simply, what will it be, e raised to I 80 plus e raised to minus I 80 by 2, and your sine 80 would be e raised to I 80 minus e raised to minus I 80 by 2i. Here 2i itself constants are there. So if you remember the method used in hyperbolic functions, you can easily derive the value of cos 80 and sin 80. Please try to do that using linearity. You can get the answer, and check whether the answer which you get using this method and the method which I am going to describe here is this thing. Okay, so the method I am going to describe here is, I am actually going to use the integral formula of e raised to ax into cos bx, which you have studied in lower classes. When you study infinite series, especially Fourier series and all, you have studied the formula of this one, e raised to x into sin bx dx, etc. We will be using that formula. Okay, I hope you remember this formula. What's the formula of this one? It is simply e raised to ax by a square plus b square into a cos bx plus b sin bx. Okay, and the formula of this one is simply identical one. It is a raised to x into a square plus b square into a sin bx minus b cos bx there. Okay, this formula you have studied in the lower classes, especially in the infinite series class. So we can directly use that formula because you know the integration there. That way also you can do. Okay, so try this both methods and try to find the answer. Okay, so if I do that one, so once you do, if you want to find integral of this, suppose you need to find L of cos 80. Okay, suppose you need to find L of cos 80. So it is integral 0 to infinity e raised to minus st into cos 80. So look at this one. So the value of this is e raised to minus st by dt is there, s square plus a square. In place of a you have minus s, in place of b you have a, so you will have s square plus s square into, you will have minus s cos 80. Okay, then plus a sin 80 plus a sin 80 here. Okay, so using this definition itself, I am writing it. Okay, so look at the definition, look at A and B, and write it carefully. Okay, so just looking in, so here actually your A is minus S here, and your B is actually A here. So you have A is minus S cos A T plus B is A here, so A sin A T. So using the definition, I am writing it here, and now you apply the limits from 0 to infinity. So once I apply infinity here, again when I apply infinity, it will be a raised to minus infinity, it will be 0 provided this s is greater than 0, so no need to look at that one. And when you apply 0, I will be getting minus of 0 is the normal limit, so it will be getting minus of e raised to 0 is 1, so it is 1 by s square plus a square, okay, into in your brackets. When you apply t as 0, you will be getting this as minus s into cos 0 is again 1, again a into sin 0 is 1, so you will be getting simply as s by s square plus a square. On a similar way, you can apply this definition here, and you will be getting the value as a by s square plus a square. And don't take my word for granted, please try to do that, apply the definition and apply this value of the integral and find the answer. Or if you can also use the method of that formula which I already told you, which is cos theta is e raised to I theta plus e raised to minus I theta by 2. Okay, so that is how you find the Laplace transform of sin 80 and cos 80. Okay, so always remember, when it is cos, you will have s on top, and when it is sine, you will have the constant on top. Okay, so if it is cos hat, you will have s by s square minus a square. If it is cos 80, you will have s by s square plus a square. And if it is sin hat, you will have a by s square minus a square. And if it is sin 80, you will have s a by s square plus a square. Okay, so now your table has 1 is there, e raised to 80 is there, cos hat is there, sin hat is there, cos 80 is there, sin 80 is there. Okay, one more thing is there. Next one is actually you are going to find the algebraic function t raised to n. Okay, so that is the next one. So with that, your table will be complete. Okay, so before that, we move on to that, let us introduce one more theorem called the first shifting theorem. It's very simple thing only. So very idea is actually good. It is actually helps you to find the problem solution in the case of inverse Laplace transform. Okay, so before I introduce that, you know that if you have L of 1, what is L of 1? Value of L of 1 is simply 1 by s. And what is L of e raised to 80? It is actually 1 by s minus a. Okay, so if you look here, actually your e raised to 80 is actually L of e raised to 80 into this one. Okay, so if you look at this, like in this picture, you can see that when I multiply this one with this e raised to 80, the transform of 1 was shifted by a quantity called a. So the transform of 1 was shifted by 1 by s minus a. Okay, so your s was shifted by s minus a. So that's the idea. So that is the first shifting theorem. So if you multiply any function with this f of t, suppose you have function f of t with the Laplace transform f of s, capital F of s. Suppose I am going to multiply this e raised to 80 with f of t, and I am going to find the transform. This will be the same as f of simply s minus a. So that is the first shifting theorem. So when I multiply with e raised to 80, in the transform, your s will be changed to s minus a. That is the meaning of first shifting theorem. I'll go to state. So this I can actually observe in the case of one here. This is because of the property of the integral which was defined in terms of this e raised to minus st. That is why. I'll show it. It's a very simple thing. So just try to understand theorem first. Whenever you multiply some function with e raised to 80, your transform will be shifted from s to s minus a. Okay, suppose your transform contains s by s square minus a square. It will be, suppose I am going to multiply. So this is the transform of cos h 80, right? Okay, suppose I am going to multiply this with e raised to bt into cos h. Suppose I need to find the transform of e raised to bt into cos h 80. So what I will do is that first I will try the transform of cos h 80. What is it? It is simply s by s square minus a square. Okay, so once I multiply this cos h 80 with e raised to bt, your s will be transformed to s minus b. So you will be getting this as s minus b by s minus b the whole square minus a square. So that is the illustration of first shifting theorem. Now let us go to the statement. Okay, so that is, suppose f of t has the transform f of s. As I told you, your f of t, the transform of f of t is f of s. Okay, then e raised to 80 into f of t will have the transform f of s minus. In place of s, we will replace it by s minus a. Okay, it's very simple thing here. If you want to prove it, so I'll just prove it. It's a one line proof. So what is your f of s minus a? First of all, your f of s minus a is actually what is your f of s? Your f of s is actually integral 0 to infinity e raised to minus st into f of t dt. Okay, so f of s minus a is actually integral 0 to infinity, looking at it is minus s minus a into t f of t dt. Just looking at f of s, I wrote f of s minus a. So this is actually integral 0 to infinity e raised to minus st, right, into e raised to at. I have splitted that e function, power function of e there, e raised to at into f of t dt, right? And what is this? This I can say that this is actually the transform of e raised to at into f of t. Okay, so that is how we write it. Or you can come the reverse way also. You can also come the reverse way. That is, suppose you need to find L of e raised to at into f of t. You can get this one, you can get this one, and you can get that also. So you can do the reverse way also. So that's the basic idea. Here you are just utilizing the power function of that e there, the integral. So that is the first shifting theorem. Okay, so the proof is given here. It's very simple thing. It's a one-line proof. So you have to understand the idea here. The idea is that whenever you multiply a function with e raised to at and find its transform, the original transform will change from s to s minus a. Okay, so that's the idea of first shifting theorem. We'll be doing this in applications. So now we have many theorems at our disposal. One is your linearity property and also first shifting theorem. So both these theorem we will be using very lavishly in applications. And also now we have a table of transforms involving one is there, e raised to at is there, cos hat is there, sin hat is there, cos at is there, sin at is there. If I can say, I will say that I also know the transform of e raised to bt into cos hat. I hope you understand. What is e raised to bt into cos hat? You know the transform of cos hat. Cos hat is s by s square minus a square. So when you supply e raised to bt, it will be s minus b into s minus b the whole square minus a square. Similarly, you can know the transform of e raised to bt into sin hat. Similarly, e raised to bt into cos at, sin at, etc. So your table has now become bigger one, and one more function is left for our table. With that, our table is complete, and then we can straight away go for applications. So that is the idea here. So the purpose of this session is actually constructing a table which we will be using in our further applications. Okay, so the next function is actually t raised to n. So the t raised to n means you will be getting maybe t square, t cube, etc. So the derivation of t raised to n is actually very difficult. It's not required for you, just because you need to know a knowledge of gamma function to find it. So just try to remember the formula. So the transform of L of t raised to n is simply n factorial by t raised to n plus 1. This is t raised to s plus n factorial by s raised to n plus 1. Okay. For example, L of t square is simply, what is it? 2 factorial by s cube. Okay. Similarly, L of t cube is, try to understand it now, 3 factorial by s raised to 4. What is L of t? L of t is simply 1 by s square. So the transform of L, so just study this formula. The derivation is not required for you because you don't know gamma function. So we will not derive this. I'll just show you the formula. It is n factorial by s raised to n plus 1. Okay. So what is L of t raised to 5? Can you tell me? It is simply 5 factorial by s raised to 6. Okay. So if I told you in your derivation, this is the derivation, this is the formula. So gamma, you need to know the definition of gamma function there. So for our purpose, when n is a positive non-negative integer, it is simply n factorial by s raised to n plus 1. Okay. So with this, we have finally constructed our table. I have written the table on next page. Let us look at the table now. Okay. So this is the table which you should know by heart. Okay. So you should know the transform of 1. If you don't know, you can easily find it out. It is 1 by s. The transform of t is, using the formula, it is simply n factorial by s raised to n plus 1. So it is 1 by s square. T square is not need to remember again if you know this one. Okay, so if you know t raised to n, you know this one. Okay, then no need to study the fifth one here. It is not required for you. For our purpose, it's not required. Just know this much. Then you should know the value of e raised to at. It is simply 1 by s minus a cos omega t. Instead of at, I am taking cos omega t. Then it will be s by s square plus omega square. Sin omega t, omega by s square plus omega square. So whenever cos comes, s will come on top. Whenever sin comes, the constant will come on top. That's the idea here. Okay, so when it's cos hat, it is s by s square minus a square, and when it is sin hat, it is simply a by s square minus a square. And here I am not going to write y e raised to at and e raised to at is like this, because you know already the shifting theorem. Okay, so that's it. So far we have studied the definition of Laplace transform. We will not be using definition everywhere except for finding this elementary function. So we'll be using this table extensively. So we know the definition of Laplace transform, and then you know the properties like linearity property is required for you, shifting theorem is required for you, and these common transforms are also required for you. So you should study these transforms, and also try to understand derivation of cos at, sin at, cos hat, sin hat, etc., because it will help you in problems. Okay, so that is the Laplace transform problem. So this is the first session. In the next session, I will actually be taking a problem session where we'll be exclusively focused on doing problems based on this section. So be careful with this section. All these ideas will be used in the next session for doing problems. Okay, so that's it. We'll stop it here. Okay, thank you.